So just to jump right in, kind of simplify as a motto. You know, we strive to make the safest, the most efficient, and the simplest products. And all of these are really just the easiest way to use energy storage. We also look to optimize as many or any power generation source on or off grid. We really want to be able to utilize pretty much any aspect of these different power sources and applications. So I'd just like to start off a little battery chemistry, and some of this you may have already heard, but it's definitely a good precursor to what we're going to go into. Oh, and just a quick side note, it looked like on the website, we had this posted as, I think, 10 to 2. That was a misprint. It's definitely not 2 hours long. It's about, or excuse me, 4 hours long. It's about an hour and a half. So we will definitely not be going 4 hours. No worries there. So this chart here is something I've used in the past all the time. Sales for just comparing different lithium chemistries, super helpful. This chart here shows all different types of lithium ions, chemistries that are actually used in batteries nowadays. So you go across and you have your different lithium types: lithium iron phosphate, lithium nickel manganese cobalt oxide, lithium manganese oxide, lithium nickel cobalt aluminum oxide, and lithium cobalt oxide. Some of these probably not used as much as others. NMC, that's a big one. You'll see NMC with things like I believe the LG Chem uses NMC. So you'll definitely see this and the cobalt oxide utilized a lot in energy storage. Now, lithium iron phosphate, if we go through this chart, kind of just quick and easy, you can see here that lithium iron phosphate, when we go through this first column of thermal runaway, so thermal runaway when something gets warm, and oftentimes can even catch on fire. You know, you hear about this in the news. We've seen it in our laptops, our cell phones getting hot in our pocket. Well, lithium iron phosphate, out of all of these different types of lithium ion chemistries, is the only one that is not prone to thermal runaway. To kind of put it lightly, it's the safest chemistry out of these right here. It's also the only one that's non-toxic. So that makes it landfill safe. We can actually recycle these batteries. The way that it actually is acquired, so we call that, you know, the mining practice, is non-abusive, or a lot of these other chemistries you're going to see have some mining practices that fall kind of into the same realm as diamonds. And that's not the case for lithium iron phosphate. As far as the cycle lives across the board here, I try to ignore this one. This is not really super relevant because this is on a cell level. So this is the chemistry itself. And we really will dig in later, but it's more important to look at what a company is warranting and not just what the chemistry is known to perform at. Ventilation requirements, and we'll skip over CO2 because we'll go way into that later, but ventilation requirements, no ventilation requirements for LFP compared to the other lithium chemistries, as well as no cooling system. So oftentimes you'll see maybe an NMC or an LCO battery will have a liquid coolant system in order to regulate heat. This gives us an advantage when we're talking about tight spaces, hotter temperatures, places that we can, you know, really utilize these batteries with no ventilation requirements whatsoever. So once we've had our lithium chemistry kind of picked out, we still need a form factor to hold this lithium chemistry when we're building out a battery. These are probably the main three right now. The pouch cell. So this one, think about a laptop. Almost all your laptops and even some cell phones are going to have the pouch cell. So this is where we would actually house the chemistry in order to build out the battery. Now, pouch cells are notorious for swelling as well as short circuit. So you can see here, this is positive and negative here, just on these little tabs. So when we put a lot in series, we actually put them all together like that. And oftentimes there's a lot of surface area here for short circuit. So we try to steer clear of these ones on large scale batteries. Prismatic, don't see these a ton anymore. I mean, they definitely show up still, but not a lot of people are still using prismatic cells. They can actually swell and crack as well, and they're just a bit cumbersome. They're large, kind of have to play with the building blocks to put them all in place. The cylindrical cell, I mean, this is the most commonly thought of battery. It's what we think of when we think of a battery often. You know, when we think of a AA battery, that technically is a cylindrical form factor. When we use lithium batteries in a cylindrical form factor for renewable energy systems and building out larger batteries, we often are going to use a larger form factor with a cylindrical form factor. So we'd have a larger battery. It wouldn't look like a AA. It looks similar, but it definitely is going to be a lot larger. Out of testing through all three of these that we've done, the cylindrical form factor has just kind of shined as far as cycle life. It actually has that built-in short circuit protection due to where the positive and the negative are. And if it's wound, you know, if the manufacturer is wounding it right, then we can definitely see no short circuit with internally of the battery as well. So that's where these kind of shine. The only downside I would say to a cylindrical form factor is due to its shape. Sometimes there'll be space cavities when we're putting a lot of them together. So I've given it away already, but SimpliPhi Power utilizes the lithium iron phosphate, or LFP. Some people even refer to it as lithium ferrophosphate with a cylindrical form factor. So again, we've kind of ran through the gauntlet on all of these different form factors, and this was the one that we've really stuck behind. As far as the chemistry, we worked with different chemistries in the past as well. So we actually started out way back when we first started the company trying some of these cobalt-based batteries as well, and found that they weren't very safe and they didn't last very long. So that's why we've made the switch to lithium iron phosphate. So I mentioned cycle life and not basing it off of the chemistry itself. It's more based off the warranty. So this is where I would say is the best value to get that cycle life and know how long the battery is going to last. We actually warranty depending on depth of discharge. So all three of our warranties are 10 years. However, they vary by depth of discharge. So the cycles will vary by depth of discharge. Now, as I know it's going to come up, so just real quick, I'll tell you, it's if you hit the years or the cycles first. And there's a way to kind of manipulate that and use that to your advantage when it comes to these systems. So at 80% depth of discharge, which is kind of our baseline recommendation, so using 80% of the batteries from full to 20% of its remaining capacity, we warranty 10 years, 10,000 cycles. At 90%, we warranty 10 years, 5,000 cycles. And at 0 or 100% depth of discharge or 0% state of charge, we actually warranty 10 years, 3,500 cycles. And I'm going to go into here in a second why you might choose one over the other when setting up a system. EOL is an important term as well. You're going to hear this a lot. End of life capacity. This is a common term in a battery warranty. So we warranty 80% capacity at that 10-year mark. Now, that seems, you know, sometimes it's tough to gauge that, but if you look into other warranties, you're easily going to see that 80% is actually fairly high for the industry. And excuse me there. Oftentimes it'll be 60 maybe, or 70 tops is what I've seen. So some other advantages to the battery itself and the form factor and the manufacturing practice and the lithium iron phosphate all being put together is we get high or wide operating temperature as well as a wide charging temperature. So the operating temperature, not as important. I mean, unless we're talking maybe a battery backup, but charging temperature, super important. 32 degrees Fahrenheit to 120 degrees Fahrenheit, we can charge or discharge the battery in. Now, unlike a lead acid battery where you'll see a lot of efficiencies on maybe the low end or the high end, we really kind of stick, no matter where we are on the spectrum, we'll still see the same efficiencies. 120 degrees Fahrenheit, we've definitely had a lot of use cases where batteries are operating either close or at that temperature on a very daily basis and had no issues whatsoever. So this wide charging temperature and operating temperature allows us to not have a need for coolant, the HVAC, or the ventilation systems. So each of our 5 batteries also comes with an integrated BMS or breaker, breaker, excuse me. So these BMS battery management systems, they are internal to the battery, so they do not connect between battery management systems. So when you have multiple batteries in a bank, they only work independently. So what does it actually do then when it works independently? Well, charge and discharge protection. So if it sees too much charge or too little charge, mostly on the too much side because there really is not a very low end of things, it knows to go into a protection mode. Short circuit protection, again, same kind of thing, and same thing with overcurrent protection. Overcurrent protection probably being the biggest one that this BMS sees. So the idea is when it sees one of these things that it does not like, or it's outside of its parameters, the BMS has the ability to actually take the cells, those cylindrical cells that we talked about, and disconnect those cells from whatever the battery is connected to. The idea here is to try to prevent damage. It can do this multiple times often before actually seeing damage, but if it continues, if the issue is maybe something is way over the top on charging and it just keeps happening over and over again, eventually you could damage that BMS's or battery management system's ability to protect. One more key feature, cell balancing. So lithium chemistry in general kind of just wants to stay out of balance with each other. They want to fight off each other and they move up and down. So we do what's called passive cell balancing. So that means you're bleeding off amps on the top end of things in order to keep all of the cells balanced. Now, I'll go back here. I mentioned that these are all on an individual level. They're internal. Well, the cell balancing that happens internally is enough to, when we parallel multiple batteries, I mean, we could parallel 60 batteries and each BMS will handle its own cell balancing, and that'll actually keep the entire bank within balance. So some key features here: power capacity, fast discharge and charge, what we'd call C/2 rate. So what is the C rate? For anyone that's not familiar, a C rate is a measure of the rate at which a battery is discharged relative to its maximum capacity. So in the example of 1C, that means that the entire battery's capacity, so let's say we're working with a 3,500 watt hour battery, we can discharge 3,500 watt hours in 1 hour. That is a 1C. Now, C/2, which is what we recommend, is just meaning 2 hours. So we can discharge the entire capacity within a 2-hour window. So in the case of our 3.5 kilowatt hour battery, it's 3,500 watt hours total. We can discharge 1,750 watts per hour for 2 hours. C/2 is pretty standard across most lithium chemistries right now, but this does not have to do with surge, which we'll go into later. So this is just talking about continuous charge and discharge. But the big advantage here, we're talking smaller battery banks to supply significant power. So when we have like a well pump or an air conditioner or anything along those lines, well, we now have the ability to power that without needing it too large of a bank. We can power those heavier power demand loads with a relatively smaller bank. Scalability and expandability. This one's huge. Scalability first and foremost, I kind of touched on it a little bit already, but these batteries that we design, at least our standard kind of 3.5 and our 2.7, well, they are be paralleled, not put in series, but paralleled pretty much, and there's no limit to it. I mean, I've seen about 70 something batteries in parallel, about a quarter megawatt of just these 48-volt batteries. So there's definitely some room to scale up with these batteries and not stifle any projects there. Expandability, this one you're not going to hear from a lot of lithium companies, but we actually allow for the battery bank to be increased later. So let's say you have 4 batteries on a site and the customer wants to add, increase their storage capacity, increase their power. You can actually go back and put more batteries on. The limit on that is about 5 years. We try to stick within that 5-year mark. So if it's past 5 years, I wouldn't go back and expand that. But as long as it's within that mark, go ahead and do it. We've got tons of systems where they have gone back and added more capacity on later. No maintenance. I mean, this is true with most lithium batteries, but still definitely true with the lithium iron phosphate. Does not need to vent. There's no off gases. It really doesn't need any kind of watering or specific gravity checks or anything like that you might see with like a lead acid. And because there's no cooling system, there's no need to keep an eye on anything like that as well. The battery actually has a very, 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 very low self-discharge rate. It's about 1% per month. So this is super helpful when we're talking about maybe a battery that's sitting in idle waiting for a grid down situation. So when we're talking about a battery backup, that's where it's super, super useful. So the battery holds its power really well and holds that energy really well until it needs to actually discharge. Some other advantages here. If you were holding some batteries for a job or anything like that, you could actually hold them for virtually as long as you need to, and you're not going to see a self-discharge, or the batteries you won't come back to a dead battery. That even in cold climates or heat, it still is proven true that this is a less than 1% per month. So real quick, before I get to the kind of more technical side of things, I just like to go through this levelized cost of energy. I know, as an installer, a lot of installers, you guys are out there selling as well as installing. So I'm always happy to kind of give the tools here. The levelized cost of energy. This is the main formula that I've used to kind of keep my point when I'm comparing apples to apples, or more like apples to oranges in this case, of battery to battery. So this equation really just shows more of an overall cost over time versus an upfront cost. So we pull out different things, different key assets to really see what the cost is. And this can be super helpful when it comes to return on investment, some ROIs, or even when we're bundling the whole thing into a solar and storage project. So this is the actual equation. Pretty straightforward. All it is the cost. So this would be the, well, depending on how you want to do this, typically I use MSRP. If you have a price sheet, obviously, with multiple different batteries on it, you could do it that way. Over the capacity. So let's say we're using our 3.5 kilowatt hour battery, we would use 3.5 here. We'd do it in kilowatt hours times the cycles that are warranted. So let's say we were using 80% depth of discharge. This number would become 10,000 times the efficiency. That's a little efficiency sign. So that would be 98% on the SimpliPhi batteries times the depth of discharge, which again, I said was 80% in this case. So if we change that to 100%, then this number would also change. Once you kind of work that equation out, you might see, even in a lead acid case, not just against other lithiums, that oftentimes the SimpliPhi battery actually comes out at a lower cost over time, over the lifespan of the battery, compared to some of your other less expensive upfront batteries. Definitely with lead acid, you'll see that. I mean, when we're talking about an upfront cost that's, thousands of dollars different for the same amount of energy storage, this equation really does show the customer that it is less expensive up front, but when looking at a more efficient battery like the SimpliPhi battery, you definitely are going to see that return on investment a lot more, a lot better in the end. So one thing to add on to this, ancillary cost, as the installer, you know what your ancillary costs are as well, so it's super helpful to add these in. That could be shipping costs. Do you have to rent anything? How much does it cost to get the trucks up there? All of those different costs can always go into it, and those costs can definitely vary by battery. Definitely varies by battery weight, by components. Do you need to call the specific company to get it commissioned correctly? Those are all different things to incorporate in there, and you can always add those on as ancillary cost, just as a straight dollar amount. So SimpliPhi products, just kind of a quick overview of what we have to offer. These are our staple batteries. These are kind of our bread and butter here. Our 2.7 kilowatt hour and our 3.5 kilowatt hour. These both come in 24 and 48 volt. These units were originally created as a simple drop-in lead acid replacement. That was the original design. Now we've used them for all sorts of different things, not just lead acid replacements, but full energy storage systems, new systems, on-grid, off-grid, tons of different applications with these batteries. Now, on that same note, we utilize those batteries. So this battery specifically, the 3.5 kilowatt hour, is utilized in a lot of our products. So in this case, this is the access unit. This is our all-in-one battery and inverter unit. It comes with the 3.5 kilowatt hour batteries inside of it and a few different options on inverters. So we'll go into those in a little bit later, but the access unit, this is about 6 feet tall. It's a NEMA 3R, so it's ready to sit outside. And it's really designed for the kind of most easy plug and play solution. I hate to say that word because nothing is truly plug and play, but that's the idea here, is a simple installation to add battery on, either on battery backup, on grid, or even off grid. I've seen these as well. These products I just like to mention, this is kind of how our company was founded actually, back in, I believe, 2006 with these products. These are portable power. You can use them for a wide assortment of things, camping, emergency power. We actually started with using these in Hollywood with the movie sets for portable power. But they do utilize the same lithium iron phosphate chemistry and the same manufacturing practices. So if there's ever any interest in one of these, just let us know. We're happy to facilitate it. But we do still sell these products, and they're kind of cool little all-in-one products. You can even add solar panels on to a lot of them. So a bit about battery sizing when it comes to the SimpliPhi battery. Let's say, just for sake of this example, we were trying to size based off of a current lead acid tank. Well, the biggest thing to consider there, and oftentimes, is the depth of discharge that's allowed. So like your traditional lead acid battery, we're talking about 50% max depth of discharge, and oftentimes I think I've seen some pretty heavy degradation even using that 50%, versus we allow up to 100% max depth of discharge. That being said, 80% is our kind of guideline, our base recommendation for depth of discharge. And then we would say that's the baseline. And depending on your mode of operation, you may choose to use a different depth of discharge. And I'll go into that here in the next slide. So yeah, I've already explained this part to you. Depending on the depth of discharge, you're gonna have a different cycle life warranty. So why would this be useful? Well, all based on mode of operation. So let's say the example of a battery backup. This is the easiest example to understand for me. In the case of a battery backup system, we are very, very unlikely to discharge that battery on a daily basis, or honestly, even on a weekly basis. So in that case, we would go ahead and use 90 or 100% depth of discharge because our 10-year warranty still stands, but we'd only get either 5,000 or 3,500 cycles warranted. We don't need more than that because truly your battery is not going to go into a full charge and discharge. It might be doing a lot of small ones, but those don't add up very fast. So in like a battery backup mode, absolutely, it makes a lot more sense to go ahead and use 90 or 100%. So like if it's on grid with battery backup, I would definitely utilize that 100% of the battery's capacity. You still have 10 years, 3,500 cycles. You're not going to hit the 3,500 cycles before that 10 years. Now, on the other side of the coin, off grid, definitely use 80% depth of discharge. We need to maximize these batteries' lifespan, and truly this battery is going to be charging and discharging every single day, if not sometimes twice a day in those off-grid situations. So that would be a good opportunity to go ahead and just use 80% depth of discharge to get that 10,000 cycle warranty. And these other ones we'll just skip over, but you get the idea. The kind of main theme here is oftentimes we'll pick our warranted cycles based solely on the depth of or the mode of operation and how that kind of plays out into the warranty. So this is just a quick example of one of our spec sheets, and I'll kind of pop over this because we're going to go into a lot of it. But if you ever need spec sheets and everything like that, I'll show you the link later of where you can pull this kind of information. A lot of our spec sheets, just kind of as a quick guide, if they are a 24 volt and a 48 volt product or any other kind of voltage like that, they're typically side by side. So you can see like max continuous discharge for the 24 volt versus the 48 volt. So, just keep in mind, if you're looking at one of these, you might be looking at multiple different batteries in one spec sheet. One thing I do want to mention is I don't think it's mentioned anywhere else in the slide. The 3.5, so our kind of larger battery, is 77.5 pounds. So, it sounds like a lot, but it's really, compared to a lot of other batteries, it's designed to be small and modular so that we can go on site and very, very easily do these installations. So one more thing on battery sizing is the inverter to battery requirement. So we really try to stay true to this, as it helps keep the battery within what we'd call the C/2, that max charge and max discharge. And that guideline is the battery should be sized to twice the inverter's output capability. So in this case, we've got a Radian 8000, an 8,000 watt continuous inverter. We would expect that the battery bank would be a minimal, it doesn't matter how big it is beyond this, but a minimal of 16 kilowatt hours. That way, if for some reason this was able to discharge 8,000 watts continuous, the battery bank could handle that. Now, I know there's situations where maybe you're using a smaller inverter or something along those lines. That's where you would just want to use. So maybe you have a 2,000 watt inverter, is the smallest you can go, and you only have one battery. So we know that we're a little bit oversized. That would be a good opportunity to go ahead and utilize, based off of the maximum discharge of the battery, we could utilize maybe some extra protection. A breaker. Some inverters can actually even be programmed on the output side of things, not all of them, but some. And to make sure that extra level of protection is there to prevent the over discharge. But kind of just as a quick rule of thumb, you're sizing a new system, battery should be sized twice the inverter's output capability. So this is just a quick example, and I won't bore you with the actual math here. But when this was let's say we were doing a lead acid replacement with the SimpliPhi battery, the biggest things to consider, and we actually have a whole guide now to how to do this step by step for both lead acid or for sizing it based off of an existing PV array for backup, or tons of different examples of how to size our batteries. And I can send those out after the presentation with the follow-up. But if big things to consider: the efficiency rate of our batteries, so 98%. You know, if we were doing a lead acid, we might need to factor in 85, something around there. Even other lithium batteries tend to have a little bit lower of an efficiency rate. The depth of discharge, so how much of the battery we can actually use. Heating and cooling losses, virtually none. As long as you're in that charging temperature window, there is no heating and cooling losses. At least not any that are notable within a calculation like this. And of course, we could rerun any load calculations. So I'll hand out those. I will send out those sheets afterwards that'll have a bit more in depth about battery sizing and how to do that in different situations. So solar plus storage and using the SimpliPhi products. I mean, you know, sometimes I get caught up that I'm just talking about a battery, but you know, in the grand scheme of things here, we're really focused right now in the renewable energy sector of solar plus storage. You know, some wind, but here in the United States, I'd say it's almost all solar plus storage right now, because that solar is so popular right now. So let's talk about AC coupling with SimpliPhi batteries first. I mean, this courtesy of Schneider Electric here, super easy to follow guide. You know, we're talking about the PV arrays already being inverted. Maybe that's your solar edge, maybe that's your end phase, you know, maybe you want to go micro, you know, whatever it may be, it's already going out as AC power to this loads panel. And then it's going into, if we were to add a battery, we would kind of just put in line the battery-based inverter that would allow for the batteries to be charged from that existing PV. Even though it's AC power, this is going to take it down to DC power and then sell off the excess still to the main load. So we're kind of just throwing a kink into the line here. And then when the grid goes down, you know, most multi-mode inverters have that automatic transfer switch built in. So we're cutting power here. We're isolating, going into island mode, and everything you see here is still online. Now, most of these multi-mode inverters can also bring back online the PV array, which is a great function when we're talking about a grid down situation. So again, everything that's on the dedicated loads panel will be covered. The grid will go into a disconnect. So AC coupling, we try to make it as easy as possible with our access unit. You know, say you've got a system that's already in place using, let's say, end phase, and you just want to go and get a quick, easy backup system, but they want a decent amount of backup. Well, I think that's really where we shine versus the other competitors, is we offer backup very scalable. So it's not just one size fits all. We can go up to some pretty heavier backup systems. But go ahead, if we had an M-phase system, we would just run it right into the access unit and then out of the access unit. So kind of easy as that, and sit outside, which is really the advantage here. So especially when we've already designed the PV array, put the PV array in place, and then the customer wants an additional, say they want 10 kilowatt hours of backup, well then we can go ahead and put this unit outside and run it in. And then if the customer decides, you know, hey, I spent this money and I don't just want a backup battery, well the beauty of our access unit is it can function as pretty much anything. It can do all sorts of different options. It can do time of use, peak load shaving, cell features, just self-consumption in general as well. And we'll go into the access, I believe, here coming up in a few more slides. DC coupled, obviously we still, with battery systems, this is kind of the original design and it still holds true. That would be the idea that we are, instead of inverting from the PV array, we're just going straight into a charge controller that just takes DC power and decides on what voltage and what current to put it into the battery. So similar design, though we're just not, we're doing all the inverting here instead of inverting here. But again, the grid goes down. This DC coupled system is still capable of going into island mode and covering, also keeping PV online, but also covering dedicated loads. So this is just kind of a more in-depth overview of that. You can see your PV going into your charge controller, charging the batteries, and then going out to both backup and to main loads panel from this right here. So this is actually, this box right here would be everything included in the access unit. This one specifically, I believe, is a Schneider access unit for a DC coupled system. So a little bit about the warranty before it looks like I might be hopping around on this these slides here, but that's okay. Temperature we've already gone through. These set points, and I'll talk more about this later, are important though. Oftentimes I get asked, how do you determine depth of discharge? It's based on voltage. So, we know that 50.2 correlates on a 48 volt battery with 80% depth of discharge. You can see the 24 volt, we would just cut it in half. And then the same thing for 90% and 100%. C over 2, again, I've already talked about this, so we'll go past it pretty quick here. But again, just referring to the max continuous charge and discharge. And that can be anything from the load rate, so the inverter's ability to pull power for different, to cover different loads, or even the array size and the charge controller output, or maybe your existing PV's output. So that's important to follow that max charge and discharge. Just quick FYI, I mean, it's in the manual and everything, and it's actually on the battery. It's on top of the battery, but these 3.5s, the most common battery, these can handle 34 amps DC per battery. So that is its max charge or discharge continuous. As far as warranty services, we try to funnel all warranties through our own tech support. So I would just recommend if you're having an issue, get on our tech line. Go ahead and we'll walk through and see if it's an issue, and then second, if there's something we can fix with it, and then kind of move through there. Okay, so let's talk about installation. So first and foremost, if you're ever looking for any documents that might become helpful here, let me pull this up. So if you're doing an installation, if you're just trying to size a system, if you're just trying to sell it to somebody, we go here, go into product documentation, and you're going to find everything that you could possibly need for that. You'll find spec sheets, warranties for each battery, the basic installation manual, which is just kind of talking about the battery itself and the access units, and then also these integration guides that kind of go through different inverters and what the language is for each of those inverters and how we would integrate with that. So I'll have a slide on those later, but this support product documentation, this is kind of where you're going to find all of your useful product documentation for installation and other things like that. So shipping and receiving the battery, it's important to check the battery for damage straight out of the box. I mean, they're in these boxes right here, so it's unlikely that damage can happen, but it definitely does happen. So we want to check that right away as the installer. Make sure not to sign off on it. Make sure to sign damage if there is any damage whatsoever. Check the breaker. If it drops, sometimes the breakers can go can be not close right. That often can be a sign of stress that it dropped on the battery. And also take a multimeter to it. So that's probably key right here. Is multimeter is your best friend. The voltmeter. Go ahead and take that voltmeter. Take it to the leads and see what you read. You should see somewhere, if it's a 48 volt battery, I would expect to see around 50 to 52 volts. Mounting requirements, we really don't have a lot of clearance or mounting requirements. So no clearance requirements as far as I know. I mean, you can put them flush up against each other. Tons of different batteries can be right up against each other. It's not a problem at all. We can also, we can mount them on the walls. We can use a battery box, a racking system. It really doesn't matter too much. There's only one orientation requirement and that would be that these battery leads here cannot be facing down. So that's kind of a newer one. I know we've had some systems in the past that we did allow for that, but the concern is that we don't want it wearing down on the electronics here in the top of the battery over time. You can put them sideways. You can put them, any orientation, just not upside down. So a little bit about wire sizing. When we're talking about wire sizing in the SimpliPhi battery, often we're talking about two different wire sizes. So we're talking about from the battery to the combiner and from the combiner to the inverter. So you'll see smaller gauge wire from the battery to the combiner, but you'll see larger gauge coming out of the combiner to the inverter if we are using a combiner in this case. Make sure all your cable lengths are the same. All your wire sizes are the same, and I got the next slide kind of goes into that a little bit better. But also, this question comes up a lot. It's a 3/8 lug on the battery. So let's skip over this one because I don't like that one as much. I'll make this available afterwards. It's great to kind of dig through, but as an easier guide to see parallel wiring, that would be this picture here. So SimpliPhi, we try to employ a different method of wiring from your typical, what you might be used to as far as wiring, definitely with lead acid batteries. So typically we go positive to positive to positive to positive up to whatever our source is or our DC bus. Same thing with the negatives, and we would really virtually be jumping from battery to battery. We recommend that you do positive up, positive up, positive up, positive up, all landing on the same common bus, all same length and same size cable, and same thing with the negative. This allows us to scale up on a larger scale, I guess, for a lack of a better word. We can scale up to these large battery banks. It also allows for the efficiency to really hold true to that 98%, as well as it just balances out the batteries better. So the power tends to be a lot more evenly distributed throughout the entire bank when we do this method. And due to that lithium nature of kind of staying out of balance, this truly helps the battery achieve that long lifespan, as well as that high efficiency rate. So, if we're talking about 1 or 2 batteries, we probably, even 3, we likely don't need to use a combiner. We might just be using a DC bus that's already on the inverter, or a common one of those. So if we have a power panel, let's say we were using like an Outback Radium with a GS load center, we could probably land up to 3 batteries on that. But if we were going to build a larger system, we'd want to use something like a battery combiner. There's tons of different options out there. Outback makes one. Midnight makes, I think this was actually the Midnight one that holds about 12 batteries on it. But they're basic, just insulated boxes with copper. That's all we need. We don't need any crazy extra protection. We just want to combine the batteries with those same length cables onto this before running to the inverter. There's tons of different options out there, and even to build custom boxes like this, I see all the time. So this is a bit different of an, so this is the same type of wiring, but the combiner is the important part here that I want to point out. This combiner does have breakers. Again, it's not required. I actually met this gentleman on one of my recent trainings. He called out his picture here, but he wanted that extra level of protection. They had a lot of lightning storms in the area, and he expected that this would actually be used with the surge protector, excuse me, and actually running the batteries into these breakers. Again, it's not necessary, but it is definitely something that you can utilize. And this is a good example too, where we can see all these batteries are running into this combiner. But then if we look, it's kind of hard to see, but if we look right here and right here, we can see there's only one positive per GS8048 inverter here. So we've combined, and then we've ran positive and negative to each of these inverters. Just real quick, torque specifications. We just want to make sure we're using the proper torque wrench, not using an impact or anything like that. We don't want to damage those battery leads. Those are the specifications right there. But over torquing a battery could possibly cause damage to those battery leads. So we really want to try to avoid doing that. If you under torque, not as serious of an issue, but you will see maybe a smaller efficiency and less distributed power. Okay, so let's talk a little bit about system commissioning. So right here this is actually a little bit out of one of our integration guides. This one appears to be the XW Plus integration guide and the Schneider charge controller. You know, we can see here that this is what I was talking about. It goes through different languages here and exactly what that setting should be. We're trying to take the guesswork out of these setups, because oftentimes when we're working with a multi-mode inverter, there's quite a bit that goes into the programming, especially on the battery side of things. So we just like to kind of spell out the language as easy as possible. One thing to note is you might see 2-stage versus 3-stage. 3-stage being a charge with a float. We only use 3-stage when it comes to charge controllers. If it's the inverter charger, so that would be like charging from the grid, charging from an existing PV array, charging from a generator, that's when we want to use 2-stage no float. So we only want that bulk and absorb charge. That's just kind of what we've utilized from now, just because oftentimes you don't want to charge from the grid or from a generator, or oftentimes even an AC coupled PV array using that 3-stage charge. So basic settings, you know, those are always in there: the absorb, the float, the low battery cutout, the high battery cutout, what the recommended is, and even goes into what it is for depth of discharge, as I kind of went over earlier, as well as some advanced functions. You know, we'll spell them out a little bit, but you might have to do a little guess and check work when it comes to things like cell or automatic generator start triggers. And I just want to quickly touch on this: the low battery cutout restrictions. Like here in the Schneider manual, you can see they only allow for the low battery cutout to go up to 48 volts. Well, I mean, that's clear that that's not what you want if you're going for 80% depth of discharge. So it's easily supplemented with things like a grid trigger or a generator trigger to come on before that. So no fret there. If you can't hit the low battery cutout that you desire, just give us a call and we'll help guide you through what setting to properly use. Quick thing about commissioning before I move on is also that this is kind of ambiguously worded in the manual, so I just like to touch on it real quick. It says that the batteries need to be fully charged before commissioning. What it's actually saying is that the batteries should be fully charged before connecting the loads. So you would want to commission the system, do all the programming that we just went over here, then let the battery fully charge, and then go ahead and connect or turn on that AC output, let the load start connecting to the battery, and then that battery covering those various loads. So charge and discharge of a lithium battery is a bit different than a lot of other batteries. It's very flat. So very, very, very flat across the board. So you can see here, you know, we're talking 48 for 0% state of charge. It's about 48 volts. For 100% resting state of charge, 52.5 or higher. It's only about we're talking about a 4 or 5 volt window here from 0 to 100. So it's definitely a bit different than the lead acid battery or even some other lithium chemistries. You also note this tail here. This one's important for customer facing stuff. We charge at 56 volts on the bulk, but we can see here that the battery is 100% at about 52.5. I've seen it more around 53 volts even. The reason for that is we charge high because we don't require an equalization. This is how we make sure that the battery gets a full charge and also stays balanced. We charge that higher end of things. The second the battery's done charging, that charger turns off, loads connect, you'll see this dip really fast. It'll go down to about 53 or maybe even a little bit lower. Completely normal. It's just how lithium batteries operate. It's going into its 100% resting state of charge. So it's a common thing we get from customers asking, why is my battery not holding that charge right at the end there? It's just not, it's already at 100%. That's just where we're charging at. It's not where it's resting. A little bit on code requirements and how they relate to batteries. I mean, I don't know, where we're at currently. I think this is probably a little old, June 9th. I could probably pull the newest one here soon, but 2017 NEC seems to be adopting pretty quick. I would expect that, we'll see a lot more of it. Definitely in this area soon. Probably not here as much. The California tends to straggle a little bit, but with that comes rapid shutdown requirements, and really not a ton related directly to the battery, but it definitely relates to our access unit. So, say we're doing a basic DC coupled system, we might need to use things like a birdhouse, shut-off boxes. There's tons of different ways to do this. Even the Tygo optimizers, those things can be utilized as rapid shutdown compliant only. They don't even need to be optimizers. But if we're working with our access unit, and this is very true for AC coupling, this is what the point I want to drive home is, if we are AC coupling, so we have an existing PV array, and this battery is just being used for on-grid backup power. Let's say you had end phase on the roof going into the access unit, it's already rapid shutdown compliant right there. Those microinverters made it rapid shutdown compliant. That's definitely something to consider when we're going through these, but we don't need to utilize the more expensive things like the birdhouse and stuff if we're just going to go with that AC coupled design with the access, and we can rely on our string or our microinverters to cover that rapid shutdown compliance. So the access, I've been talking a lot about it, and now we can actually kind of dig through it a little bit. So again, this is utilizing the 3.5 kilowatt hour batteries. It's pre-wired, it's pre-programmed. NEMA 3R, so it's ready to sit outside. It's really designed for a quick installation. Application-wise, we're talking about new installations, DC coupled, sure. AC coupled, probably the most common for it. So existing PV arrays, outdoor installations, huge one. If they can't put it inside, maybe the system needs to stay outside. This is an easy solution to cut out the work on the installer side of actually going through and building out a cabinet for somebody, as well as an introduction to an energy storage system. So maybe you've worked a lot with grid-tied systems in the past. You've had customers ask you, I want to get a battery backup on this system. Well, we've taken all the guesswork out. We've done the wiring. We've made it as easy as possible. So these are the two access units that we're currently offering. So this is the Schneider access unit, and this is the Outback access unit. So just different inverters, different hardware in each one. And I'll kind of go into what the key features are of these two units. So with the Schneider unit, we're utilizing the 6848XW Plus as the inverter charger. That's 6.8 kilowatts continuous, has a max surge capacity of 12 kilowatts, and 140 amps DC charger built into it. Now the Schneider, let's go back here. This one is, we can AC couple with this one. Currently, we're not AC coupling with the Outback access unit. So that's where this charge controller here is actually an optional feature. So the Schneider 80 amp 600 volt MPPT charge controller is an optional add-on if you want to go DC coupled. But it's kind of a cool charge controller. It does 600 volts in, so it kind of mimics what I would consider a string inverter, but it's all DC still. It's not actually doing the inverting. It's just powering the batteries. And it's 80 amps DC max charge current, so about 4.8 kilowatt array. The Outback, that access unit, that we are utilizing the GS8048A. This is missing an A right here, but it is the newest model. This is a big inverter. It's 8 kilowatts continuous, has a max surge of 16 kilowatts, and 115 amp DC charger built into it. It's Rule 21 compliant. This is really only relevant if we're talking about California or Hawaii. So I know a lot. This is a lot East Coast here, so we'll run past that real quick. It also comes standard with these 2 charge controllers. So as I said, the Schneider unit can be AC coupled, so the charge controllers are optional. This Outback unit right now is only DC coupled, so it does come standard with 2 of these FM80 charge controllers. So that's 8 kilowatts of max PV this thing can handle, 80 amps DC per charge controller, and 150 volts max PV voltage input. So some smaller strings, you will need to do some combining, but again, this one's DC coupled only. So this is just a rundown of DC and AC coupled with the access. I've kind of already gone through this. So we've already talked about, here's your AC coupled array already being inverted going into the access. Here's your DC coupled array with that optional charge controller. But now let's talk really quickly. Here's the grid, and probably even a main loads panel here. The access has a built-in transfer switch. So you do not need to add any kind of transfer switch or anything like that. This unit will sense grid down. Both units will, either the Schneider or the Outback access will sense grid down and go into island mode. So that's automatic, and that happens on its own. Just really quick to go through the different options. Let's talk Schneider unit first. So with the Schneider access unit, we have 3 different sizing options for this one. We have 7 kilowatt hours, we have 10.5 kilowatt hours, or 14 kilowatt hours of energy storage. Comes standard with that inverter charger, so the 6848 XW Plus. And it also comes standard with system control panel, but you can always go with CommBox to make it be able to connect to the internet and actually see monitoring capabilities and things like that. Optional, again, because it can be AC coupled, it does not come with the charge controller. So the charge controller is actually an optional feature, as well as the automatic generator start. So AGS is not ready out of the box. That is an optional thing as well. I already talked about the CommBox. And then we can also parallel units. So if we want to put 2 units side by side, that's totally fine. I've seen 3. I don't think it's a great idea. I think at that point you might as well start pulling the pieces out and building out a system. But it has been done. Optional battery cabinet as well. We do have an optional cabinet that does not, it's not an entire new unit. It's just that NEMA 3 enclosure with room for 12 additional batteries. So we can add on more energy storage, but keep the same level of power. The Outback variation, this only comes in one size right now. It's 14 kilowatt hours. Because of the size of the inverter, this is about the minimum we want to add for batteries. But it does come standard with the Radian GS8048A, 2 FM80 charge controllers because it is DC coupled, the Outback Mate 3S, which is kind of the control, the brain of the operation, the Hub 10 where everything's connected and the AC sync occurs, as well as this unit, this GS8048A, has room for a 2-wire generator out of the box. There's really not a lot of optional features of this one. Everything just kind of comes standard as is, and DC coupled again. You can parallel these units as well as add on more battery capacity with that optional battery cap. So a little bit about installing these units. They do ship on their sides just for safety. So they ship without, the batteries come with it, but they're not inside of the unit. They're not connected to the cables when they arrive. So let's, I don't want to jump back too many slides, but just to give you an idea, I think it's useful. So these batteries will just be out of the unit when it arrives, and then these cables are already connected here. So all you're doing is just connecting to the terminals. That's the only connection point there. So it's about 700 pounds of that battery. It's definitely not light. It is an NEMA 3 enclosure. It's thick. It's, everything's already in the unit, so it will require a few people to get that unit into place. As far as the site location goes, indoors, not as popular. I'll tell you that right now. I've not seen a ton of them indoors, but it's totally fine. There is no off-gassing, no chance of thermal runaway. The unit can absolutely sit inside. It can sit in a garage, a basement, a utility room. It can sit in the living room if you really want. Outdoor, now that's more common. Because of its NEMA 3 rating, we see it outside very, very often. So that's kind of the main installation location. But as far as heating and cooling, not really required. I mean, obviously dependent on your area. If you're like way, way, way up north, you might want to consider how often the battery is being used. The inverter itself has a decent amount of heat that comes out of it. That will keep those batteries fairly warm if we're talking about, let's say it's 20 degrees outside, 20 degrees Fahrenheit outside. Well, it's going to be a lot warmer in that battery cabinet. Heat-wise, I've never seen an issue with it whatsoever. We've got a ton of units in Puerto Rico, Florida, I think even maybe some other South American countries, we have some as well. So really, it's not a big deal when it comes to heat. It's white, so it reflects the sun really well. But there is a fan here. If it does get too hot, it'll pull some air out of that. Pad requirements for the concrete pad. We do recommend mounting it on a concrete pad. So 4 inches thick concrete. It should be 3 inches wider than the access unit on each side. It should be level or secured, obviously. And then we want to secure it down with concrete anchors. So this is the big part of the installation here. Once we move it on site, we go ahead and use these knockouts. So on the bottom of the unit, I mentioned already, the batteries do not go inside the unit right away. So we can actually access these knockouts from inside the unit, knock them out, drill the concrete anchors through instead of having to try to fit into this little space to drill the concrete anchor. That way they're really secure, really easy, and then we would plug these holes afterwards and maintain our NEMA 3R rating. As far as clearance and knockouts, on that same kind of topic, not knockouts related to these ones, but different ones. There's 3 inches of clearance on the sides is required, unless there's 2 accesses side by side. They can be flush up against each other. 3 feet of clearance in the front. Got to have the door able to open, as well as some fire code stuff. And as far as knockouts go that are already on the unit, so not these ones, but ones for running things like PV or AC out, there's 4 on each side. One of them's an inch, and one is an inch and a half, and then the other 3 are 1 inch. If you ever need more knockouts, I mean, we can always work to get, guide you through popping another knockout in a safe spot on the unit. But typically, those 4 tend to be plenty. System programming. So, it comes set with basic SimpliPhi settings. I mean, if you were to take it out of the box and not mess with it, the system would operate just fine. If you want to change things based specifically on customer preference, mode of operation, maybe you just like you've worked with the Schneider or the Outback before and certain settings that you like to manipulate a little bit, you can definitely go in and change those settings based on that mode of operation. You can always use the manuals to kind of guide you through different modes of operations and what different set points you might want to set. So if it's a battery backup where they don't want to use any of the power until the grid's down, that's where you might want to say, okay, maybe I should go ahead and set rebulk a little bit higher. So different things like that, and we're always willing to help with guiding that extra programming. But out of the box, it is pre-programmed. Post installation. So let's talk about this. So this is the Schneider. We'll do this one first. The Schneider wireless gateway. So we just utilize the inverter company's wireless capabilities to monitor these access units. So this shows historical monitoring here, so you can kind of go back in time, see what things were, how things were affected. This is a great tool for troubleshooting or just seeing kind of how your energy usage plus how your PV has been performing. Here, we can see real-time data. We can see how much solar we're producing. We can see what the loads are pulling, even where the battery's at, and different things like that. So, you know, super helpful. The customer can get this right on their phone, have this available to look at, and even you can have it as well as the installer to really keep an eye on these systems. Outback, very similar here. So we have our historical monitoring here. We've got our real-time monitoring here. The big advantage of the Outback optics is so if we're using the Outback access unit, we will actually be able to go into device map here and physically change settings as the installer without going on site. The Schneider cannot do that right now. So it is really helpful when maybe you have a site that's a couple hours away, and if the customer calls and says, you know, I actually changed my mind. I really don't want the battery discharging every day. I just want it to hold its charge. Well, luckily you can go in then, just sit at home. You could lay in bed and do it, hit device map, go ahead and change the settings just remotely. So that's definitely a nice feature of the optics already. This one actually comes up a lot post-installation. What do I need to tell the customer? What do I need to do as the installer? Not a lot. They're maintenance-free batteries. There's just not a lot that needs to happen. Not really a lot of calibration. You can take some direct readings every now and again if you want. You should, see some pretty even voltages across the board. If it's something looks irregular, let us know. But I wouldn't say this is something anyone needs to do on a monthly basis or probably even a yearly basis. I mean, the batteries are very maintenance free, so not a lot of maintenance involved in them. If you do need help troubleshooting and all, let us know. We kind of have this troubleshooting guide for when things start getting a little bit more complicated to pinpoint. Often we're talking about with troubleshooting, these are large systems, and often we're only the battery supplier. We try to educate our tech support as much as possible on all different aspects of the solar system, how it all connects together, whether it's grid tied, off grid, all of those different components, so that they're a little bit better at, keying in on what might be the issue, even if it's beyond the battery. As far as battery issues, there's some common ones that are not issues. These are indicators, I would call them. First would be the battery break. If it's tripping, that's often a sign of overcurrent. So if it's been in place for a while and all of your breakers keep tripping, it's the battery trying to tell you that you're putting too much current into it. So don't ignore it. Definitely give us a call right away if that's happening on multiple occasions. Low battery cutout events, these are totally normal. The inverter goes into a state of low battery cutout. If the battery is still functioning, but the inverter's in standby, that's a function of the inverter, and that's totally normal. Now the BMS open circuit, the bit harder to diagnose here. So say that your battery stopped providing power through these cables and this breaker never tripped. Well, oftentimes that means that the battery management system saw something it didn't like, and it actually went into an open circuit. So you would toggle the breaker to bring that back online. But again, that's an indication that something is not right in the system. Somewhere it's being overcharged, over discharged, something along those lines. So it's important to give us a call right away. Other than that, I mean, that's pretty straightforward. Taking direct readings is key. If there's an event as the installer, my first thing would be take a multimeter to the battery, each battery individually, the entire bank, because readings you're going to get from the inverter or the system or even the access unit during these events is not as accurate during these events as the battery itself with the multimeter. Always feel free to email our tech support or call our tech support. And if you can't get through, sometimes we're really busy, just helping commission and things like that, and there's not a ton of tech support people. Feel free to always reach out to our main line, and they'll get you in touch with either an apps engineer or myself, and we can always guide through things. So I want to talk real briefly. It looks like we've got about 15 minutes, and I do want to get to questions. So I'm going to go through the new products, and then I'm going to skip over the case studies. so that we can answer. It looks like we got a decent amount of questions. So new products, these were at SPI this year, SPI 2018. This is the Express unit. It's kind of the half access unit. It's a smaller version of the access unit. This one comes with the Magnum inverter. It comes with an optional, or the charge controller actually just comes standard on it. So this is the DC inlet. So you can go ahead and take a kilowatt, maybe 2 kilowatts, plug it in, charge up the batteries. Then it also has a AC inlet here for charging from things like shore power, or even it just has 4 outlets if you want to charge straight from the grid. This is designed to be mobile. It's still NEMA 3R, even though it's on wheels. So you can move it around, let it sit outside. I mean, there's some key functions here of this unit. Maybe the customer doesn't really want to go ahead and set up an entire PV array just for backup power, or they don't want to rewire of their loads panel, and they already have an existing PV array. Well, we can just charge straight from the outlet. And because of the low self-discharge rate, we can store this away in the garage or wherever it is, and only pull it out when the power is down by just connecting loads directly into the unit through these outlets. So there's 4 outlets here, and there's also 2 USB ports here as well for charging. The DC inlet is detachable. So if you have a PV array, like maybe let's say you had 1 or 2 panels that you wanted to charge this from, you could plug it in and then detach it when it's charged and bring it somewhere else as well. Kind of a cool unit. It's smaller designed. It comes in 2 different sizes, 5.4 kilowatt hours and 7 kilowatt hours. Now, the smaller version can only do 120 volts AC, and the larger version can do 120 to 40 AC. So keep that in mind. This smaller 5.4 is not meant for larger appliances. We also have this product. It was at SPI as well. It's not, this one here is ready to ship as of now. I mean, these are in production, ready to go. This one, it's close. We've been doing a lot of real world testing with the unit. So, we're working on projects already with it, but we would expect to see that before 2019 to actually be available to ship. However, some of these larger scale projects take a while anyway, so it's okay. This is our high voltage. We call it the microgrid here. I would say it's both microgrid and commercial and industrial backup. So this unit, unlike our other units, these are the same battery modules, those 51.2, the 48 volt battery modules here, but you can stack them in series for the desired voltage that you want. So it could be anywhere between 200 volts to 800 volts DC nominal. Capacity wise, 16, I think 0.5 is the lowest you could go on this unit, up to 2 megawatt hours of storage with this unit. So BMS is external actually, so it has communications protocol, Modbus, CAN bus, Ethernet. If you have like a large, let's say you get a call from a grocery store and they want backup power for the refrigerators, but they're using a 480 3-phase panel. This unit's great because we can go ahead, maybe they want a megawatt of backup, and we would tie it to one of those larger industrial inverters like the Princeton Power, the Ideal Power, Dyna Power, all the larger ones that can do that 480 out. So same thing though, again, same battery, same chemistry, it's still lithium iron phosphate. Comes on this rack, that's standard, it comes like this in the racking system. We do have a container option as well. So if you say, I know I need 10 of these stacks, I need 500 kilowatt hours of storage, and I don't want to build it myself, we can actually build it out in the container with the disconnects and everything built into it and ship it that way so that it comes on site, configured and everything for your desired voltage and storage.